In this video, we're going to cover Taylor and Maclaurin series. First, we have a note. It says to determine whether a function has a power series representation, start by working backward. Suppose f is any function that can be represented by a power series. So we have f of x equals c sub 0 plus c sub 1 times the quantity x minus a, plus c sub 2 times the quantity x minus a squared, plus c sub 3 times the quantity x minus a cubed, and so on. Next, we're going to take the derivative of f, and all of the c sub 0, c sub 1, c sub 2, and so on are constant values. So the derivative of c sub 0 is 0. When you take the derivative of this expression, you're just going to be left with c sub 1. And to take the derivative of the rest of these terms, you're going to use the chain rule. So you take this 2 and you multiply it to the constant in front, so you get plus 2 c sub 2. You leave the inside the same, x minus a. We subtract 1 from the exponent, making just a power of 1. Then we times by the derivative of the inside, which the derivative of the inside is 1. So you times this by 1, which is just itself. Similarly, when you take the derivative of this term, you're going to get 3 c sub 3 of the quantity x minus a to the power of 2. And then you times by the derivative of the inside, which is just timesing by 1. And then if you took the derivative of the next term, you would get this expression. To find the second derivative and the third derivative of f, you use the same process. Next, it says if x is equal to a, we take a and plug it in for x, and then we'd plug it in here, and so on. When we do so, it's going to make all of these terms cancel so that f of a is just equal to this c sub 0. Similarly, for the first derivative, when you plug in a for x, all of these terms will cancel out, so you get f prime of a is equal to c sub 1. Same thing on the second derivative, when we plug in a for x, these terms will cancel, so we get that f double prime of a is equal to just this front term, 2c sub 2. And the same thing for the third derivative, when we plug in a for x, these terms cancel out, and we just have this first term. So you can see the third derivative of f, when you plug in a, you're just left with 2 times 3c sub 3. And then you're probably noticing that there's a pattern. This can be written as 0 factorial of c sub 0. This we can write as 1 factorial c sub 1. Right here we can write this as 2 factorial c sub 2. And then we could think of this as 1 times 2 times 3, so that would be 3 factorial c sub 3. And then finally, if you think of this as f of a equals 0 factorial c sub 0, and if you isolate the c sub 0, you end up getting that c sub 0 equals f of a divided by 0 factorial. Similarly, right here, if you isolate the c sub 1, it's going to be equal to f prime of a divided by 1 factorial. Also right here, if you isolate the c sub 2, it's going to equal the second derivative of f at a divided by 2 factorial. And then you see the same thing here for c sub 3. So therefore, in general, the coefficients can be written as the following. C sub n is going to be the nth derivative of f, plug in a, divided by n factorial. And this leads us to the definition of a Taylor series of the function f at a, or you can say about a, or you can also say centered at a. So your Taylor series is written as f of x equals, you have sigma notation, n starts at 0, goes to infinity. This represents the nth derivative of f at a. You divide by n factorial times the quantity x minus a to the power of n. So first, when you plug in 0 for n here, here, and here, you get just f of a. When you plug in 1 for n, you get f prime of a over 1 factorial times the quantity x minus a to the 1. When you plug in 2 for n, you get f double prime of a over 2 factorial times the quantity x minus a squared. And then you just follow that pattern for n equals 3, and then n equals 4, and so on. This is the formula for the Taylor series of f, and it's at a, or we also call it centered at a or about a. So whatever the value is for a, you plug it in right here, and then it's also x minus a. So for example, if a was 5, this would be x minus 5. If a was negative 3, it would be x plus 3. Okay, and then we're going to go on. It says for the special case where a is specifically equal to 0, the Taylor series becomes a Maclaurin series of the function of f. So the formula stays the same, which is really nice. You still have f of a plus f prime of a over 1 factorial times x minus a to the 1, plus f double prime of a over 2 factorial times x minus a to the 2. But you can see that 0 is plugged in for a. And this becomes your formula for the Maclaurin series for the function f. And again, for a Maclaurin series, a equals 0. This example says find the Taylor series of f of x equals 1 over x, and this problem is centered at a equals 1. So I set up a graphic organizer for us. Our first column is n, so we start when n is 0. So that means we're not going to take a derivative, you just start with the given function, so f of x is equal to 1 over x. And 1 over x is the same as x to the negative 1. And I'm also going to write it as 1 over x. And since this problem is centered where a is equal to 1, we're going to plug in 1 into this function. So when you plug in 1 right here, you just get 1 divided by 1, which is 1. Okay, next n is equal to 1. That means we're going to take the first derivative. So we're going to take this -1, multiply it to the front, and then subtract 1 from the exponent. So we get -2, and then I'm going to rewrite this, and then we're going to plug 1 into the function. So 1 squared is 1, and then -1 divided by 1 is -1. Next, n is 2, so we're going to take the second derivative. So we bring this -2 and multiply it to the front, and then we subtract 1 from the exponent. And then we'll rewrite this as 2 over x cubed. And then we plug in 1 for x. For our next row, we're going to take the third derivative, and then we'll rewrite that as -6 over x to the fourth. And then finally, we plug in 1 for x, so we get -6. And we're actually going to do one more row. So we're going to take the fourth derivative, and then we rewrite this as 24 over x to the fifth. And then finally, we plug in 1 for x. And then I just want to point out over here, this follows a very specific pattern. 1 is equal to 0 factorial, -1 equals -1 factorial, 2 equals 2 factorial, -6 equals -3 factorial, and 24 equals 4 factorial. Okay, so now at this point, we're going to write out the formula for Taylor series. And again, this problem is centered around a equals 1. So again, our Taylor series formula is f of a plus f prime of a over 1 factorial times the quantity x minus a, plus f double prime of a over 2 factorial times the quantity x minus a squared, and then so on. So again, we're using that formula, but we're plugging in 1 for a. All right, so you can see that I wrote it out, and anywhere there was an a, I plugged in 1. And then our next step is this f of 1, f prime of 1, f double prime of 1, and f triple prime of 1. We get those values from this table right here. So remember, f of 1 is going to be 1, f prime of 1, that's right here, and f double prime of 1, again, that's right here. F triple prime of 1, we can find that right here. And again, you're probably noticing that these coefficients are all going to cancel out and just become the value 1. So we end up getting that f of x equals 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed, and so on. So our last step is f of x, which equals the original function 1 over x, can be rewritten in sigma notations. You'll notice the first term is positive, the second one is negative, the third one is positive, so the terms are alternating. So we start off with sigma n equals 0 to infinity, and then we go -1 to the n. And then you'll notice this first term does not have an x minus 1, so technically that could be x minus 1 to the 0. This is x minus 1 to the 1, x minus 1 to the 2. So we just write x minus 1 to the n. So here's our Taylor series for the function 1 over x. This example says, find the maclaurin series for f of x, which equals e to the x, and find the radius of convergence. So first, since this is a maclaurin series, a equals 0. So for our chart here, we're going to start with n equals 0. So that means we just use the original function, f of x equals e to the x. And then we plug 0 into the function, so e to the 0 equals 1. Next, we'll do n equals 1. So here we take the first derivative, and the derivative of e to the x is just e to the x. And then again, if we plug in 0 for x, we get 1. Next, we have n equals 2, so we're going to take the second derivative. And again, the derivative of e to the x is itself. And when we plug in 0, we also get 1. All right, and just for fun, I did this one more time for n equals 3. And now let's go ahead and write out the maclaurin series for f of x equals e to the x and a equals 0. So remember, the maclaurin series is the same as the Taylor series, it's just that a is equal to 0. So when we write out the formula f of x equals f of a plus f prime of a over 1 factorial times x minus a to the 1, plus f double prime of a over 2 factorial times x minus a to the 2, and so on. But again, for all of the a values, we're going to plug in 0. Okay, so here's the maclaurin series written out, where we have a is equal to 0. And then what we want to do is we want this f of 0, f prime of 0, f double prime of 0, f triple prime of 0. We want to replace all of those with this column over here. So f of 0 is equal to 1. F prime of 0 also equal to 1. Same thing for f double prime of 0. So again, we replaced all of the numerators with the values from this right column. So you can see that here. And then finally, we want to rewrite this in sigma notation. So we have f of x equals e to the x, and then we have our sigma, n starts at 0, goes to infinity. And you'll notice this first term doesn't have an x, so technically that could be x to the 0, then x to the 1, then x to the 2. Also, you're probably noticing that in the denominator, this factorial is the same value as the power. So we write that as x to the n divided by n factorial. And then finally, we're going to find the radius of convergence. So to do that, we're going to use the ratio test, and then this is our a sub n. So it starts the limit as n goes to infinity, the absolute value, and then it's going to be a sub n plus 1 divided by a sub n. So for a sub n plus 1, I plugged in n plus 1 anywhere there was an n, and then we divide by a sub n, which is the same as multiplying by its reciprocal. So right here we have n plus 1 factorial, so that can be rewritten as n plus 1 times n factorial. And then that's helpful because now these n factorials cancel. Right here, this is x to the n plus 1. We can rewrite that as x to the n times x to the 1. And then these x to the n's cancel. So you're left with this x to the 1, and I'm going to bring that to the front of the limit. And remember, it's still an absolute value. And then all we have left here is 1 divided by n plus 1. Because n is going in the positive direction, we can drop the absolute value. And then this limit, as n gets larger and larger, this fraction is going to go to 0. So the absolute value of x times 0 is just 0, and 0 is always less than 1. That means that this series is convergent for all real numbers. Therefore, the radius of convergence is going to be infinity. So again, we get that r equals infinity. This example says find the Maclaurin series for f of x equals sine of x for all x, and then find the radius of convergence. So the first thing we want to note is because it says Maclaurin series, that means that a is equal to 0. So I have that written here, and then we'll start our chart with n equals 0. So we just have f of x equals sine of x, and then we plug in 0 for x, and sine of 0 is 0. Next, we're going to take the first derivative. So the derivative of sine is cosine. And then we plug in 0 for x, and cosine of 0 is 1. So now we take the second derivative, and the derivative of cosine is negative sine. Then we plug in 0, and we just get 0. We take the third derivative, so the derivative of negative sine is going to be negative cosine. When we plug in 0, we get negative 1. And since we have these zeros over here, and remember this column represents the values that get plugged into the numerator on our formula, we're going to take this out 2 more rows just so we can really see a pattern. All right, so now we're ready to plug in 0 for a into our formula. So I have it written out. We have f of 0, and then we have f prime of 0 over 1 factorial, and then this is technically x minus 0 to the power of 1. Here we have f double prime of 0 over 2 factorial, and again, this is technically x minus 0 to the power of 2. Then you can see the term with x cubed, the term with x to the 4th and 5th. So then we take these values and we plug them in into the numerators. So again, we plug in 0 right here for f of 0. We plug in 1 for f prime of 0. We plug in 0 for f double prime of 0. We plug in negative 1 for the third derivative of 0. And then again, this 0 gets plugged in here, and this 1 gets plugged in here. So you can see by plugging in these values, what happened is all the even-powered terms collapse, and then we just have the odd-powered terms left. And then in addition to that, the odd-powered terms are alternating. So I just rewrote it without the zeros, and so you can see it a little bit better. And finally, we're going to rewrite this in sigma notation. So we have that f of x equals, and the original function was sine of x. So we have sigma, and then we start with n equals 0 to infinity. The first term is positive, so we write negative 1 to the n. And then because it goes x to the 1, x to the 3, x to the 5, these powers are going up by 2. So we write x to the 2n plus 1, and I just want to verify when we plug in 0, you get 2 times 0 plus 1, which makes 1. When you plug in 1, you get 2 plus 1 is 3. When you plug in 2, you get 2 times 2 is 4 plus 1 makes 5. And again, the factorial matches the power on the x. So there's our sigma notation. And next we're going to identify the radius of convergence, and we'll do that by using the ratio test, and then here's our a sub n. So we have the limit as n goes to infinity of the absolute value, and then this is a sub n plus 1, where anywhere there was an n, I plugged in n plus 1, and then distributed the 2 and then combined like terms, so you get 2n plus 3, same thing in the denominator. And then you divide by a sub n, which is the same as multiplying by its reciprocal. Remember, because we have absolute value, this negative 1 and this negative 1, they'll essentially cancel out. Right here, this x to the 2n plus 3 and x to the 2n plus 1, the x to the 2n's will cancel, so then all we have left is x cubed over x to the 1, and that makes x squared on top, so we can pull that to the front of the limit. And then this 2n plus 3 factorial, you can rewrite it as 2n plus 3 times 2n plus 2, and then times 2n plus 1 factorial, where this factorial and this factorial cancel out. So here we have the limit as n gets larger and larger, this fraction is going to go to 0. And 0 is less than 1, therefore our series is always convergent. So again, our radius of convergence is going to be r equals infinity. This example says find the Maclaurin series for cosine of x for all x and find the radius of convergence. So here we have a note. It says instead of making columns like the ones we used on the front with n and then the derivative and then the derivative where we plugged in a, we're instead going to use the sigma notation that we just found for sine of x, and then we'll use that and take the derivative of it to find cosine. So we have that cosine is equal to the derivative of sine, and then this is the problem we just did. We have that sine of x equals, and this is 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then it keeps going. So since sine equals those terms, we'll write them here. So again, cosine equals the derivative of sine, and sine, I have it written out here, and then we also have its sigma notation. So we're going to do term by term differentiation. So the derivative of x is 1. For the derivative of x cubed, it's going to be 3x squared. The derivative of x to the 5th is 5x to the 4th. The derivative of x to the 7th is 7x to the 6th. And then when we take the derivative of this sigma with respect to x, we're going to look at this term right here. So the derivative of x to the 2n plus 1. We bring the 2n plus 1 and we multiply it to the front, and then we subtract 1 from the exponent. So next we're going to reduce the fractions. Remember, 3 factorial means 3 times 2 times 1. So this 3 and the 3 on the bottom are going to cancel. And remember, 5 factorial is 5 times 4 times 3 times 2 times 1. So the 5s are going to cancel as well. And then same thing over here with the 7s. And again, when this 3 cancels with the 3 on the bottom, you're still left with 2 times 1, which is the same as 2 factorial. And then same thing here, the 5s cancel, but you're still left with 4 times 3 times 2 times 1, which is 4 factorial. And then over here, this 2n plus 1 cancels with this 2n plus 1, and then that leaves just 2n factorial. So this is your series or sigma notation for the function cosine of x. And then for our radius of convergence, I just wrote out since sine of x converges for all x, so does cosine of x. So again, for cosine of x, the radius of convergence is r equals infinity. This example says evaluate the indefinite integral, and we have the integral of sine of x over x dx as an infinite series. So the first thing I want to do with this indefinite integral is this x right here. I want to pull it to the front as a 1 over x. And next I'm going to take the sine of x and rewrite it as a series in sigma notation. So here we have sine of x is equal to, and we have our sigma, and we have our negative 1 to the n, and then x to the 2n plus 1 over 2n plus 1 factorial. So this x right here has a power of 1. If we bring it back into the series, it's going to be x to the 1 in the denominator. And that would cancel with this x to the 1 right here. So now that we have our sigma condensed as the integrand, we're ready to integrate. It's an indefinite integral, so we're going to have our arbitrary constant c, so I just put that in the front. Then we have sigma, n starts at 0, goes to infinity. I just dropped down this negative 1 to the n. When we integrate, remember we have this x to the 2n, so we're going to add 1 to the exponent. And then we divide by the new power. So we're going to bring this 2n plus 1 and put it in the denominator. And then we still have this 2n plus 1 factorial also in the denominator. And here's our final answer. This example says obtain the Maclaurin series for the following functions. Part A, it says f of x equals e to the negative x over 2. All right, so I want to point out we're not going to fill out the whole chart because right here we have e to a power. It's a composition of functions, so what we can do is we can take the Maclaurin series formula for e to the x, and then instead of x, we're going to substitute negative x over 2. All right, so I wrote the Maclaurin series for e to the x for reference. We have e to the x equals, and you have sigma x to the n over n factorial. So again, for this function, because we have e to this power, we're going to take this negative x over 2, and we're going to substitute it in place of this x here and here. So you can see negative x over 2 is plugged in for x. And then at this point, we're dividing by n factorial, which is the same as multiplying by its reciprocal. So I wrote the numerator, and then we're timesing by 1 over n factorial. And then finally, I'm going to take this negative and pull it to the front as negative 1 to the n. And then we'll have x to the n on top. And then in the denominator, we'll have 2 to the n times n factorial. So there's our final answer. For part B, we have f of x equals x times cosine of x. This time you'll notice we don't have a composition of functions, but we do have a product. So what we want to do is we're going to leave this x here, and then we're going to replace cosine with its sigma notation. And cosine is where we have x to the 2n divided by 2n factorial. And finally, we're going to move this x to the 1 back in. So when we go x to the 2n times x to the 1, it's going to make x to the 2n plus 1. So we have our sigma negative 1 to the n, and then we have x to the 2n plus 1 divided by 2n factorial. For this example, we have cosine of 2x. So we want to identify which of these series represents cosine of 2x. So I have cosine of x written out here. Remember, cosine of x has the negative 1 to the n, and then it's x to the 2n over 2n factorial. So when we have cosine of 2x, this is a composition of functions. In place of x, we have 2x. So that means we can take 2x and we can plug it in right here for x. So again, to find cosine of 2x, I set up our sigma, and then right here is supposed to be x, but instead of x, we're going to substitute 2x. So we'll start by plugging in 0 for n, and you just get 1. Then we're going to plug in 1 for n, so you get negative and then 2x squared over 2 factorial. Then we plug in 2 for n, so you get 2x to the 4th over 4 factorial. And we could keep going, but you can see that the answer is going to be D. This example says a power series representation for e to the x squared minus 1 all over x is, and we have our multiple choice options. So there's a couple of things going on here. First, we have the function where x squared has been plugged in for x. Then that function is being subtracted by 1 and divided by x. So first I have the series for e to the x here for reference. Again, instead of x, we have x squared. So we're going to plug x squared in for x here and here. And then next I want to take this series and expand it. So first we plug in 0 for n. Next we plug in 1 for n, so that's going to make x squared over 1 factorial. Then we plug in 2 for n, and then plug in 3 for n. All right, so here's the series for e to the x squared. And what we're going to do is we're going to take this infinite series and we're going to substitute it right here in the fraction. So we're going to take all of these terms, plug it in right here, and then we subtract 1 and divide them all by x. So let's go ahead and get that set up. So we have e to the x squared minus 1 all over x, and it equals, and I took this whole thing and plugged it in for e to the x squared right here. Then we still have minus 1, and we still have divided by x. So you can see what happens is this 1 and this 1 cancel out, and then all of these terms, we're going to divide them by x. So x squared over 1 factorial divided by x just leaves x over 1 factorial, or just x. Then we have x to the 4th over 2 factorial divided by x, and that's going to make x cubed over 2 factorial. And right here, x to the 6th over 3 factorial divided by x is going to make x to the 5th over 3 factorial. And again, we could keep going, but you can see that our answer is going to be B. All right, so again, there's our answer. This example says the coefficient of x to the 4th in the Taylor series for e to the 4x about x equals 0 is, and we have our 4 answer choices. I wrote out our series for e to the x for reference. So for this problem, we have e to the 4x. And again, hopefully you're noticing this is a composition. So that means instead of x, we're going to plug in 4x. All right, so I plugged in 4x for x right here. So we'll go ahead and start by plugging in 0, then we'll plug in 1 for n, then we'll plug in 2. When we plug in 0, we get 1. When we plug in 1 for n, we get 4x over 1 factorial. When we plug in 2 for n, we get 4x squared over 2 factorial. And then I'll keep plugging in n equals 3 and n equals 4. And this problem wants the coefficient of the x to the 4th term. So our x to the 4th term is right here, and the coefficient is going to be 4 to the 4th over 4 factorial. All right, so this is just the coefficient of the x to the 4th term. And I'm going to write this out, and then I'm going to reduce the fraction. So the 4's cancel, and then I'll cancel this 2 with one of the 4's. So we end up getting 32 over 3. So our answer is D. All right, so there's our final answer. This example says the Taylor series for sine of x about x equals 0 is given x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus ... If f is a function such that f prime of x is equal to sine of x squared, then the coefficient of x to the 7th in the Taylor series for f about x equals 0 is... So we have a lot going on here. First, I just wrote f prime of x equals sine of x squared. This is the series for sine of x. And you'll notice right here we have a composition of functions. So we have x squared in place of x. So we're going to take x squared and we're going to plug it in right here for x. So this represents f prime of x, but the problem wants the coefficient of the term x to the 7th for the Taylor series of f. So that means we're going to take this series f prime and we're going to integrate it. So we're going to take the integral of f prime. So that means we're going to take the integral of these terms. So I'm going to write them out. We have x squared, we have minus x to the 6th over 3 factorial, and then plus x to the 10th over 5 factorial. So let's go ahead and integrate this. So the integral of x squared is going to be x cubed over 3. And then when we integrate this term, we're going to add 1 to the exponent. And then we divide by that new exponent. And we'll do the same thing for this term. And this works out great because the problem wants the coefficient of the x to the 7th term. Here's the x to the 7th term, and again, we just want the coefficient, which is going to be -1 over 7 times 3 factorial. So the coefficient is -1 over 7 times 3 factorial, and again, 3 factorial is 3 times 2 times 1, or 6. So we get -1 over 42. So our final answer is A. Alright guys, thanks so much for watching, and I hope this video helped you with Taylor and Maclaurin series. So please subscribe to my YouTube channel and hit the like button on this video.